Hello everyone, this is Dr. G. Pranita, Assistant Professor of Chemistry working in Government Degree College for Women, Begumpet, Hyderabad. Today I am going to explain the very important topic, that is valence bond theory. Last class we were discussed about Werner's theory and Sedgwick theory. In the Sedgwick theory there were few drawbacks are there. To overcome those drawbacks, next a new theory came out. The theory is called it as a valence bond theory. This theory was explained by Linus Pauling in 1931. According to this theory, mainly this theory explains the structure and magnetic properties of a large number of coordination compounds. So coming to the silent features of this theory, here the central metal atom or ion has the required number of vacant orbitals for accommodating the electrons which are donated by the ligand. Because in formation of the coordination compounds, metals will involve as well as ligands will involve. Here, almost all the D block elements will involve to form the coordination complexes. All the D block elements are having the vacant d orbitals to get the required electrons which are donated by the ligands. Here for the metals, the vacant orbitals may be s orbital, p orbital, d orbital or f orbital. This vacant orbital goes hybridization to form same number of hybrid orbitals in the presence of ligands. So metal is having these vacant orbitals. So in the presence of ligands, these vacant orbitals undergoing to hybridization and produces the same number of hybrid orbitals. The number of vacant orbitals is equals to the coordination number of the metal ion for a particular complex. Suppose if the number of vacant orbitals are 4, then the coordination number of that particular complex is 4. Suppose if number of vacant orbitals are 6, then the coordination number of that particular complex is 6. So each ligand has at least minimum donate at least one lone pair of electrons to the metal. And also here, vacant hybrid orbitals filled with a ligand to form coordination bond. So while forming the complex, metal is acceptor, whereas ligand is a donor. Metal is having the vacant orbitals, and these number of vacant orbitals undergo hybridization in the presence of the ligand and produces the same number of hybrid orbitals. That number of hybrid orbitals is equal to the coordination number of that particular complex. So these are the some silent features of the rules of the valence bond theory. If you see, the geometrical shape depends upon the hybridization of the metal orbitals. Here, for example, if you see here, coordination, if any complex coordination number is 2, according to valence bond theory, if any complex coordination number is 2, then hybridizer orbital sp, that means one s orbital will involve, one p orbital will involve, then the geometry of that complex is linear. For example, here silver complexes, these two are examples which are showing the linear geometry. Whereas if any complex which are having the coordination number is 3, then that particular complex hybridization is sp2 hybridizer orbital. sp2 is nothing but here in this one s orbital is involved and also two p orbitals are involving for the hybridization. So here total 1, 2 p orbitals, total 3 orbitals are involving for the hybridization. Hence, always according to the valence bond theory, number of hybridizer orbitals is equals to the number of the coordination number. So the shape of this particular geometry, this complex is trigonal planar. So this is the example for this complex. Whereas suppose if the coordination number is 4, then hybridizer orbitals are sp3. That means here one s orbital and 3 p orbitals will involve. So geometry of this particular hybrid this complex is tetrahedral. So these are all examples for the tetrahedral geometry. In all these examples here, the coordination number of in all these complexes, coordination number is 4. Suppose if you see this example, nickel tetracarbonyl, here 4 is the coordination number of this particular complex. So this geometry of this complex is tetrahedral, and in this complex, this metal is undergoing to sp3 hybridization. Similarly, here also in all these examples, coordination number is 4 and the metal is undergoing to sp3 hybridization and coordination number is 4. Suppose if the coordination number is 4, so in some metals they are showing the undergoing to dsp2 hybridization. So if the complex is showing the dsp2 hybridization, then the geometry is called it as a square planar. Here in these two complexes, coordination number is same 4 4, but here metal is undergoing to sp3 hybridization, whereas here metal is undergoing to dsp2 hybridization. If metal is undergoing to dsp2 hybridization, then the geometry of that particular complex is square planar. So generally nickel, platinum, palladium, all +2, nickel +2, platinum +2, palladium +2 complexes generally will involve in a square planar complex rather than tetrahedral complex. Nickel +2, platinum +2 and palladium +2, all these metals will form the square planar complex rather than forming the tetrahedral complex. So in these complex also, this coordination number is 4, but here the metal is undergoing to dsp2 hybridization. So the geometry of this complex is square planar. Suppose if any complex the coordination number is 5, then the hybridization of that particular metal is dsp3. One d orbital, one s orbital and 3 p orbitals, total 5 orbitals are undergoing to hybridization and involves the dsp3 hybridization. The geometry of this particular complex is trigonal biplanar. And whereas here these are the examples for the of that particular complex. And here if you see here also, we already studied the coordination number is 4, maybe the sp3 hybridization or maybe the dsp2 hybridization. If dsp2 hybridization, the geometry is square planar. If sp3 hybridization, the geometry is tetrahedral. Whereas for sp3 hybridization, the coordination number is 5, then the geometry is trigonal bipyramidal. Whereas if the coordination number is 6, then molecule metal may undergoing to sp3d2 hybridization or d2sp3 hybridization. Whenever the metal complex will involve in a sp3d2 hybridization, then this hybridization is called as an outer orbital hybridization. That means nd orbitals will involve. Whereas if the metal is involving into d2sp3 hybridization, then this complex will involve into inner orbital complex. The inner orbital d orbitals will involve in this formation of hybridization. So in the both the cases, whereas sp3d2 as well as d2sp3, in both the hybridization, the geometry of this complex is octahedral. So here, if the participation of n minus d, suppose if in a metal, if n minus d, that is 3d orbitals will involve in the hybridization, then that it gives the inner orbital complex or low spin complex. Suppose if a nd orbitals, that is 4d or 5d orbitals will involve in the hybridization process, then it gives outer orbital complex as well as high spin complex. Here inner orbitals are nothing but those are 3d orbitals. Low spin is nothing but which are almost diamagnetic. Here 4d or 5d orbitals are called as a outer orbitals. Here high spin is nothing but which is a paramagnetic. Suppose if any complex, if the metal is involving inner orbital d orbitals, then that is diamagnetic. Whereas if any metal involves in outer orbitals, that is those are 4d or 5d, then that complex is a paramagnetic. Whenever strong field ligands like ammonia, cyanides are involved in the formation of complexes, they cause a pairing of electrons present in metal ions. This process is called as a spin pairing. That means in the presence of strong field ligands like ammonia or cyanide, single electron will become paired in the presence of these ligands. This process is called as a spin pairing. For example, if you see the geometries of corresponds to the coordination number 4. If the coordination number 4, the geometry may be the tetrahedral geometry and the geometry may be the square planar geometry. First, let us see the tetrahedral complex compounds. For tetrahedral complex compounds, the coordination number is 4 and hybridization is sp3 hybridization. For example, if we see this complex here, formation of nickel tetrachloride. Nickel tetrachloride. In this complex, first nickel hybridization valence electrons, nickel metal valence bond hybridization 3d8 4s2 because nickel atomic number is 28. So valence bond outermost electronic configuration is 3d8 4s2. And here in this complex, 4 Cls are present. So x minus 4 is equals to minus 2. So in this metal will get plus 2 oxidation state. So plus 2 oxidation is nothing but we have to remove the 2 electrons from this total electrons. So whenever we remove the 2 electrons from this total electrons, so finally it will get 3d8. So this is the nickel plus 2 ion electronic orbitals here, because in this 3d8 1 total d orbitals are 5 1 2 3 4 5 next 6 7 8 total 8 electrons are present, whereas s orbitals became 0 because of having the nickel. In this complex, nickel is having the nickel existing as nickel plus 2. So here it is 4s orbitals, whereas here these are 4p3 orbitals. These are vacant orbitals. And also here chloride is a weak ligand. So weak ligand, in the presence of weak ligand, this ligand is not able to do the pairing of these electrons. So these electrons will be remain in each orbital. So in the presence of this ligand, this metal is undergoing to one s and 3 p orbitals will combine and forms the sp3 hybridization. And now in this metal is having the sp3 hybridized orbital, vacant orbitals, and in these hybridized orbital, each ligand donates one lone pair of electrons. So here total 4 ligands are present. For each orbital, each ligand donates one pair of electrons, so that it forms the complex by forming the 4 bonds between the chlorine and nickel. Like this it forms. So this is the formation of nickel tetrachloride. First we have to take the nickel electronic configuration, that is 3d8 and 4s2. In this complex, nickel is existing as a plus 2. So we have to remove the 2 electrons here. Finally, it will get 3d8. And here 3d8 is nothing but this is the nickel plus 2 electronic configuration. And this is the chlorides are the weak electrons. So in the presence of weak electrons, no electron pairing takes place. So which involves in sp3 hybridization. In these vacant orbitals, each ligand donates one pair of electrons and makes the bond between chlorines and nickel. So here, after formation of the complex, it forms the electronic configuration. It will become like this. If you see the structure of nickel tetra, here I have given, this is the structure of the tetrahedral geometry, because nickel tetrachloride, which involves in a sp3 hybridization. For sp3 hybridization, the geometry is tetrahedral geometry. So tetrahedral geometry looks like here nickel, whereas here 4 chlorines are present. So this is the geometry of nickel tetrachloride. And here in this complex, total 2 single electrons are present. Hence, this complex is a paramagnetic complex. For example, if you see the complex nickel tetracarbonyl, in this nickel tetracarbonyl complex, formation of this complex, here also 4. In this complex, the coordination number is 4. That means which may involve either sp3 hybridization or dsp2 hybridization. Here nickel electronic configuration, as we know, 3d8 and 4s2. But in this complex, there is no charge on the sphere, as well as carbonyl is a neutral ligand. So no oxidation number of this metal, no charge of this metal. So we have to write as it is these electrons in whenever while writing the electronic configuration of the nickel. So here completely, so this is the total 8 electrons here, 3d8 as well as 4s2, 3d8 and 4s2. Here, because here the carbonyl group is in strong ligand, so in the presence of the strong ligands, what will happen? Electron pairing will take place. So whatever the two electrons are here, two electrons will come here and it takes the pairing. So because of the pairing of these electrons, this orbital will become empty, and the empty s orbital and 3 p orbitals will undergo into hybridization and forms the sp3 hybridization. So in this sp3 hybridization, here these 4 carbonyls, each carbonyl which donates the one lone pair of electrons, which is a neutral ligand, and makes the bond with the nickel. So like this, it forms the tetrahedral geometry. And here in this complex, if you see, observe here in this electronic configuration, no orbital which is not having single electron. Hence, all electrons are paired. Hence, this complex is a diamagnetic complex. Earlier, in this example, final complex, these orbitals are having the single electrons, hence it is a paramagnetic complex. And also here weak ligand, so no pairing of electrons will take place. Whereas here it is a strong ligand. In the presence of the strong ligand, pairing of electrons will take place, and also no single electron is present in the single orbital, hence it is a diamagnetic. And these two are examples for the tetrahedral geometry to coordination number 4. This is the nickel tetracarbonyl. Here 4 COs, each ligand will donate the one lone pair of electrons to the metal and forms the bond between the ligand and metal. Here, according to the valence bond theory, there is a bond formation between the metal and ligand is the covalent bond. Whereas Sidgwick theory, he was explained the bond formation between metal and ligand is coordinate covalent bond. But here he was explained, Linus Pauling, he was explained the bond formation between metal and ligand is the covalent bond. This is the geometry of the nickel tetracarbonyl, and these two are example for the tetrahedral geometries. Whereas in this another example, zinc tetrahydroxide, in this example also, in this one, in this metal, zinc is existing as a zinc plus 2. So zinc atomic number is 3d10 4s2. Final electronic configuration is zinc. Final electronic configuration is 3d10 4s2. So here, whenever in this complex zinc is existing as a plus 2, hence all the 3d10, so 4s2 is become empty, because of when we remove the 2 electrons, it will become empty. So these 3 orbitals will involve in a hybridization and forms the sp3 hybridization. To each orbital, ligand donates, this OH minus is a monodentate ligand, donates the electrons to here each orbital and make the bond between metal and ligand and forms the tetrahedral geometry. These 3 are the examples for the tetrahedral geometries. So here this complex also diamagnetic, because no orbital is having the single electron, hence it is also diamagnetic complex. Whereas the geometries corresponds to the coordination number 4. So the geometry of these complexes are square planar complexes. Earlier we have studied the coordination number, which is having the tetrahedral geometry. Here the complexes which are we are seeing the square planar complexes. Square planar complexes are nothing but the metal which involves in a dsp2 hybridization. For example, if you see in this complex here, this is the nickel tetracyanide. Nickel tetracyanide, nickel atomic number is 28. So hybridized nickel electronic configuration is 3d8 4s2. 3d8 4s2. Whereas in this complex, because 4 cyanides are present, so 4 minus on the charge which is having the 2 minus, x minus 4 is equals to 2 minus, so nickel will get the plus 2 charge. +2 charge means whenever nickel is existing as a +2, we have to remove the 2 electrons from here. So it will get 3d8, 4s0 and 4p0. This is the nickel electronic configuration, whereas here it is the nickel +2 electronic configuration. So in the presence, whenever ligands coming closer to this metal, that is nickel, this cyanide is a strong ligand. Cyanides are very strong ligands. So in the presence of the strong field ligands, these electrons undergo into pairing. Pairing takes place, and this orbital, this d orbitals will become empty, and this d orbitals also, one d orbital, one s orbital and two p orbitals will involve in a hybridization and forms the dsp2 hybridization. Now to this to each orbital, one of the ligand donates the electrons, pair of electrons, and makes the bond between this metal and ligand and forms the nickel tetracyanide complex. So this is the geometry of the nickel tetracyanide. This geometry, this shape is called as a square planar. Whereas if sp3 hybridization is involved, then the geometry is tetrahedral. Here dsp2 hybridization is participated. Hence this geometry is called as a square planar geometry. Here this oxidation number is +2 and each ligand donates 2 electrons. So in the presence of the strong field, here what will happen? Because of the pairings takes place, so no single electron is present. Hence it is this complex is a diamagnetic complex. So how do we see? First we have to take the nickel atomic number, that is 28. Then we have to take the electronic configuration of the nickel, that is argon 3d8 4s2. In this complex, nickel is existing as a +2 charge. So whenever we take the nickel +2 to electronic configuration, then it will become 3d8 4s0 4p0. So it will become like this. Whenever cyanides are coming closer to this nickel, this cyanide, as cyanides are very strong field ligand, hence in the presence of the strong field ligand, these electrons coming pairing takes place, and here it will become empty. So here one ds, the two p orbitals are going to hybridization and forms the dsp2 hybridization. To these four orbitals, four ligands donates the electrons and forms the square planar complex. If you see the another example here, platinum tetrachloride. Here also, platinum outermost electronic configuration also D8S2, because nickel and platinum both are belongs to the same group. So here D8S2. So whenever here in this complex also platinum, because which is having the 4 minus charges, x minus 4 is equals to 2 minus, then the charge of this platinum is equals to +2. Whenever we remove the 2 electrons from the D8S2, so it will become D8. Then whereas here D8 is nothing but it will become like this: 1 2 3 4 5 6 7 8. But here chlorides are weak field ligands. In the presence of weak field ligands, actually the pairing of electrons should not take place. But always nickel +2, platinum +2, palladium +2, these metals are trying to get the square planar geometry only. So even though which is having the weak field ligands, in the presence of this also, this here pairing takes place, which involves in a dsp2 hybridization. Even though in this complex which is having the weak field ligand, actually whenever here it is a weak field ligand, it should involve in a sp3 hybridization. But here this platinum complex, platinum +2, palladium +2, nickel +2, always they try to get the dsp2 hybridization and forms the square planar geometry. So in this complex also all the electrons are paired, hence it is also diamagnetic complex. So here if you see the hybrid orbitals and bonding in a square planar complexes, here for example if you see in this complex, here nickel nickel which is having the D8 electrons, and whenever D8, 3D8 and 4s2, in the nickel plus 2 only 3D8 electrons are present, 4s0 and 4p0. In the presence of cyanide, because cyanides are strong field ligands, in the presence of this ligand, these electrons undergoing to pairing takes place, and this orbital, one of the d orbital will become empty, dsp2. These four orbitals will involve in a hybridization and makes the bond with the ligands, and finally forms the square planar complex. Like this, square planar complexes and tetrahedral complexes will form. Coming to the octahedral complexes, in the octahedral complexes, if n minus 1 d orbitals are used for the hybridization, then the complex is called as a inner orbital complex. Whereas nd orbitals will involve in a hybridization, then the complex is called as a outer orbital complex. Inner orbitals are complex. Orbitals are nothing but 3d orbitals, whereas outer orbitals are nothing but 4d orbitals. Suppose if inner orbitals will involve to form the complex, then that is called as a low spin or spin paired complex, or it is also called as a diamagnetic complex. Whereas outer orbitals will involve while forming the complex, then this complex is called as a outer orbital complex or high spin complex or spin free complex, or also we can call it as a paramagnetic complex. So while forming the octahedral complexes, these two orbitals either depends on the metal, may involve n-1d orbital or may involve nd orbitals. So let us see some examples of octahedral complexes. Here the geometry corresponds to the coordination number 6. Here octahedral complex compounds, for example, if you see the formation of hexaamine cobalt. In this hexaamine cobalt, cobalt is a metal. This outer electronic configuration is argon 3d7 4s2, because cobalt atomic number is 27. So this is the 3d7 4s2. In this complex, ammonia is a neutral ligand. So whatever the charge is present on the sphere, that is equals to that metal oxidation number. So cobalt plus 3 is nothing but we have to remove the 2 electrons from here, 1 electron from here. So it will become 3d6. So how to write the 3d6 electrons here? Because total d orbitals are 5. In each orbital 5 first we have to fill up 1 electron, then we have to fill pairing. So this is a 3d6, 4s0, 4p0. So here, as ammonia is a strong field ligand, whenever come close to this metal, in the presence of this ligand, strong field ligand, these electrons will become pairing, takes place the pairing. So as pairing takes place here, in this d orbitals, total 2 d orbitals, one is dx square y square, another one is the dz square. Total these 2 d orbitals will become empty, and d2sp3 D2sp3 hybridization takes place. In this D2sp3 hybridization, 2 d orbitals, 1 s orbital, 3 p orbitals will undergoing to hybridization. So total, what is the coordination number here? 1, 2, 3, 4, 5, 6. Total 6 orbitals undergoing to hybridization and forms the D2sp3 hybridization. So here, because which are having the total 6 vacant orbitals, to each vacant orbital, one of the ammonia ligand will donate the electrons and makes the bond between the ligand and metal, forms the octahedral complex. So in this one, this complex hybridization is D2sp3 hybridization, and this complex geometry is octahedral geometry. Whereas in this complex, which orbitals are participated? n-1d orbitals, that means 3d orbitals are participated. Hence in this geometry complex also call it as a inner orbital complex, and also call it as a diamagnetic complex. Same here, the representation of the octahedral complex. Here this is the geometry of the octahedral complex. So in this octahedral complex, total coordination number is 6. Whereas in this example, hexacyanoiron, in this hexacyanoiron, iron atomic number is 26, so argon 3d6 4s2, and in this case metal which is having X and also 6 minus charges are present, -6 is equals to -3. hence metal will get +3 charge. So we have to remove the 3 electrons from here. So it will get 3d5 4s0. So writing of electrons in the orbitals like this. So whenever in the presence of the cyanide, in the presence of, as this cyanide ligand also strong field ligand, in the presence of this ligand, these electrons are undergoing to pairing takes place. So it will become like this. So here also 2 d orbitals become vacant. Those are d x square y square d z square. So here 2 d orbitals, 1 s orbital and 3 p orbitals will involve in a hybridization and forms the d2sp3 hybridization. And to this each orbital, again ligand donates the electrons and forms the complex. So in this complex, the hybridization is d2sp3 hybridization, and here 3d orbitals are involved while formation of the complex, hence it is called as a inner orbital complex. Inner orbital complex, and also it is called as a but here it is having one vacant, this orbital is having one single electron, hence it is called as a paramagnetic substance, because it is, this orbital is having one single electron. Suppose if they are having the paired electrons, then those complex is a diamagnetic, but it is having the one single electron, hence it is the paramagnetic complex. Coming to the geometry of this octahedral complex, here it is a metal, whereas the 6 ligands are accommodated like this. This geometry is called as the octahedral geometry of this complex. Whereas in another example here, hexaamino cobalt +3, here also cobalt, which is having cobalt atomic number is D7S2. D7S2. Here also, in this case, it is a neutral ligand, so cobalt is +3 charge. So here, whenever we remove the 3 electrons here, so finally we will get like this. Finally, we will get like this. So D2sp3 hybrid orbitals will involve. Hence, it is also inner orbitals are involved, inner d orbitals are involved while formation of the complex, and here all the electrons are paired, hence it is the diamagnetic substance, and the hybridization of this complex is D2sp3, and the geometry of this complex is octahedral geometry. This is the structure of hexaamino cobalt. This is the octahedral geometry. Whereas if you see this example here, it is the hexafluorocobalt. In this hexafluorocobalt, here cobalt atomic number is 27. So electronic configuration of the cobalt is argon 3d7 4s2. In this complex, cobalt oxidation number is +3. That means we have to remove the 3 electrons from here. So it will become like this. But here in this complex, fluorides are weak field ligands. So whenever in the presence of the weak field ligands, the electrons won't take place the pairing. So here no pairing takes place, no d orbitals are empty, 3d orbitals are empty, hence which is involving 4s, 4p and 4d orbitals are involving in a hybridization and forms the sp3d2 hybridization. This hybridization is called it as a outer orbital hybridization, because here in this complex fluorides are weak field ligands. In the presence of the weak field ligands, here no pairing takes place. So here outer orbitals, outer d orbitals are involving in the hybridization, that is called it as a sp3d2 hybridization. So here also this geometry of this complex is octahedral geometry. Here in this case, in this each orbital is having one single electron, hence this complex is a paramagnetic substance. Like this, in some orbitals, some complexes which may show inner orbital complexes, maybe 3d orbitals will involve. In some complexes 4d orbitals or 5d orbitals will involve, then those complexes are called as a outer orbital complexes. So like this, Venner's theory, valence bond theory explains the structure and magnetic properties of the many coordination complexes. But even though this theory has some drawbacks. Coming to the drawbacks of this theory does not explain the color of coordination compounds. That means all the coordination complexes are showing the many different colors. Why that complexes are showing the colors, this theory does not explain. And also this theory does not explain magnetic behavior based on geometry. And also this theory does not explain why some call inner orbital, why some call having the outer orbital complexes, even though the same metal ion in the same oxidation state. Fails to predict the exact geometry of the complexes with the coordination number 4, because if the coordination number is 4, some geometry which are having the tetrahedral geometry, then another according to the X-ray which is showing like a square planar, it fails to explain the geometry which are having the same oxidation number and the same metal, and does not distinguish which are weak field ligands and which are strong field ligands. And also this theory cannot predict the exactly the tetrahedral and square planar structure of O4 coordinate. And also this theory does not explain the stability of the complexes. So these are the few drawbacks of the valence bond theory. So again, to overcome these drawbacks of the valence bond theory, new theory came on. That theory is called as a crystal field theory. So today we have completely discussed about valence bond theory and how the metal complexes will form with coordination number 4, coordination number 6, like tetrahedral geometry, square planar geometry, as well as octahedral geometry, and what are the drawbacks of the valence bond theory. Okay, thank you for your patience listening.